Okay, let's start. Can everybody hear me up there? Can you hear me? Okay. So I want to continue with regular expressions, finite automata, and some properties of regular expressions. So we mentioned that regular expressions could be made by composition rules. The base cases are simple, and then of course you have the union, the concatenation, the clean closure of regular expressions. Those are also regular expressions. And we proved that you can minimize regular expressions via this example, ongoing example, make less states. And there's a famous algorithm that does this automatically for any regular expression. First you convert it to a finite automata. The finite automata could be minimized, and you end up with a minimum number of states. You can do that pretty efficiently. Minimizing a Turing machine or a push-down automata, we haven't talked about those yet, but minimizing those is actually not possible in general. It's undecidable. There's no algorithm for it. It's like the halting problem. And then we said that regular expressions in finite automata have a one-to-one correspondence between them. For every regular expression, there's a finite automata whose language is the language denoted by that regular expression. And conversely, for every finite automata, the language that it accepts is denoted by some regular expressions. You can convert one to the other pretty mechanically and straightforwardly. And the proof for converting a finite automata to a generalized regular expression entails first completing all the transitions that aren't there with epsilon transitions from every state to itself and from every state to every other state that doesn't have a transition with a empty set transition or empty language regular expression. So generalized finite automata, instead of having symbols on the arcs, they have regular expressions more generally. And you can make a transition based on anything that's denoted by that regular expression. Once you do that, you can always find a triangle of states, three states, Qi, Qj, and some Q prime in red, where these are the regular expressions on these arcs, P, R, S, and T. And what you can do is you can substitute, instead of going through this Q naught with these three arcs, R, S, and T, what you can do is go with a single arc, eliminating that state, and instead have R, as many S's as you want, because it self-cycles over here, and then finally a T. So going through Q prime is the same as going directly from Qi to Qj, but through an R, S star, T transition. How many get that? So simple transformation. And you can always apply it again and again. What's happening is now you can merge these two arcs. Instead of going from Qi to Qj with a P and then separately with an R, S star, T, you can then union both of them together into a larger regular expression, and so we collapsed these two arcs into a single arc. The point is we keep simplifying the finite automata. Now there's less states, less arcs, and you can always keep doing that. Recursively or inductively, or repeatedly I should say, you can actually do that over and over again until you have just one arc left with one big giant regular expressions on it. And that regular expression on that remaining last arc is the regular expression denoting the entire language of the finite automata. Because every transition, every transformation like that reduces the states and the arcs, but without changing the actual language of the regular, or the finite automata. So that algorithm here, and it is an algorithm, and you can run it pretty efficiently, comes up with a regular expression that denotes the language recognized by the entire original finite automata that you started from. Right? How many get this technique? Okay, pretty good. Any questions about that? So this establishes, again, a theorem. This says that any finite automata can be converted to a regular expression that's equivalent. Any issues or questions? Yeah. Yeah, so we start with some triangle of three states, and there's plenty of triangles in the graph. Why? Because what we did at the beginning, we took this machine and we added all the transitions that were missing there. We made it into a complete graph, including all the self-arcs. So all the self-arcs are there right now with epsilons. All the arcs that weren't there originally are now there with the empty set on them, which means they can never be triggered by anything. Right? So now we have a complete graph. So in the complete graph, every three nodes is a triangle. Every three nodes have three edges between them. So pick one of that triangles, and instead of going from here to here with a P and here to here separately with an R here, an S here, and a T there, These letters denote regular expressions of whatever these arcs are labeled with right now. They just denote the regular expressions happen to be on the arcs right at this moment. So instead, collapse this arc, and this state into a new arc, saying it's equivalent to going here R once, S any number of times by invoking it repeatedly, and finally T by exiting the Q naught and then going to the QJ there. And so instead of these three transitions here, I have one transition that goes RS star T. And that counts for all possible ways of making that trip with as many times around the S as you'd like by having an S star there. S star means any number of S's, including 0. Okay, that's all. So once you do that, you end up with a giant regular expression. The machine only has two states at the beginning, at the end. The first state, the initial state, and the final state, and one giant, monstrous regular expression on that single remaining arc. And that's the expression that denotes the language of the original machine. Okay, so it's a relatively straightforward transformation. We generalize finite automata to having transitions that are invoked by regular expressions now, not just individual symbols. But in general, you don't do that. Like when you use JFlap, like in the assignment and so on, you don't worry about regular expressions on arc. You just have individual symbols one at a time, and you do what it takes to construct the machine. All right, so in the book, there's the picture, what I just showed you. Right? And there's that triangle, R and S and T. They use different labels here. They use R1, R2, R3, and so on. How many see that this picture here is exactly what I showed you on the previous slide? Okay, just drawn differently without the fancy colors. Okay, so you should be reading the book. How many are reading the book, reading sections from the book? You should. I mean, the homework refers to the book, right? There's problems that come from the book in the homework, so if you're not reading the book, I'm not sure how you were able to do the homework, right? Okay, so you should be reading the book a lot. Here are some regular expression identities. These are always true regardless of what the regular expressions are. The first one says that the union is commutative. R plus S is the same as S plus R, like addition or multiplication. Not every operation is commutative. Name an arithmetic operation that's not commutative. Subtraction. What else? Matrix multiplication, or even simple division. A divided by B is not the same as B divided by A. One is not the same as the other, right? So, but, union preserves commutativity, or, So the second one is a distributive, or it's associativity law, right? RST is the same as RS, and then T concatenated to that. So concatenation has associativity as a property, right? The third one is distributive law of concatenation over union. So R concatenated to S union T is the same as R concatenated to S, separately unioned with separately R concatenated to T. It's the same thing. It's like in arithmetic, multiplication distributes over addition, right? How many understand that? So it's true here for these other operations of concatenation and union. Here it associates or distributes in the other direction too, from the other side, but very similar law. The empty set start is simply the empty string taken as a language, right? So I should probably have braces around this epsilon here, just to make sure that the type is correct. Okay, the empty set is the identity element with respect to union. So take the empty set, union that with anything, you get that thing back. And the empty string is the identity element with respect to concatenation. Just like 1 is the identity element with respect to multiplication, and 0 is the identity element with respect to addition, and every other operation has an identity element too. Right? For matrix multiplication, the identity element is a big matrix with 1 down the diagonal and zeros everywhere else. So another couple of identities, R star star is equal to R star. If you star it twice, doesn't do you any much good. Starring it once is enough. You already get everything that's obtainable by starring it. R plus epsilon start is the same as R star. This was probably the least obvious of all these identities on the screen here. This one says that R star, S star, star, the king closure in this order is the same as unioning them together, R and S, and then starring the union. So these 3 stars are replaced by a single star once you union them together. Now, none of these are definitions. They're identities, which means they're theorems. They follow from the definitions. You should be able to prove each and every one of these. Not too hard, pretty straightforward. From the definitions, these almost fall out of the definitions. The last one is probably the least trivial, but still, a one-paragraph proof will establish the truth of the last identity there at the bottom. Any questions about these? Yeah.
Okay, so the two red ones, the first one makes sense to me. The second one, I'm having trouble, like, what would our...
Okay, so in red here, I'm showing you two non-identities. So first, I'm saying here, the real identity is the empty string is the identity element with respect to concatenation. That's established here. But here, what I'm saying is the empty string is not the identity element with respect to union. Just like 0 is the identity element for addition, but 0 is not the identity element for multiplication, and vice versa. 1 is the identity element for multiplication, but not for addition. So that one, pretty good, right? Straightforward. How many see the first one, right? You had the empty string in. It may not have been there before, so you might have changed the overall result. Now this one is less obvious. R concatenated to the empty set. What is that equal to? So here I'm saying it's not equal to R, but what is it really equal to if it's not equal to R? Yeah. The empty set. How many say the empty set? Yeah, and if you're not sure, again, the way to resolve these things is go back to the definitions. So the definition of concatenation, what is it? You take everything from the first set, everything from the second set, in all possible ways, pairwise, and concatenate them together and throw them into the resulting concatenation. That's the concatenation of both sets together. So follow that definition. Take everything from R and everything from the empty set. But there's nothing in the empty set. It's empty. That's why they call it the empty set, right? Because there's nothing there. So there's no way to take something and something else at all. So what kind of a set do you have if the criteria for membership is never met for any possible element? You do have a set, but it's a set of nothing, of no elements whatsoever, because none of them meet the criteria for participation in that set. So that's why it's the empty set. That's kind of a technicality. Okay. Question? So R is a regular expression, but it denotes a language that is a set. So I'm glad you brought it up, because now we're into types again. So let's not make type errors. So R is not a set, but a regular expression. This symbol here, the empty set, is really, in this context, it's not a set either, actually. It's a regular expression denoting the empty set. Remember the definition of regular expressions just a few slides ago, right? The empty set is a regular expression. It's also the empty set. And we use the same symbol for both, and perhaps we shouldn't because it overloads it. But we're already overloading symbols, right? This plus here doesn't mean addition. It means union. So in the context of numbers, plus means addition. In the context of sets, plus means union, which is not the arithmetic addition operator, but it's kind of similar. The union for sets is sort of the analog of adding things together with multiplicities eliminated, because the set doesn't have multiple elements that are the same exact element. So, but again, don't worry too much about it. If these are technicalities, as long as you understand what's going on, you know, an occasional type error could be forgiven, right? As long as we all know what we're talking about in general. Okay, does that answer probably answers more than you wanted to know when you asked that question? But still, it's good to nail these things down. Any other thoughts or questions on these identities or everything else so far? Yeah. The closure of what? It could also be the positive closure. So for R plus S, that could be R plus, not necessarily union. So it could be concatenation of R plus, as opposed to just union. Right here, you mean? Yeah. So why would we use that as well, so R and S are regular expressions. The plus means the union. So in the parentheses is another regular expression. The plus, the star of that is yet another regular. So all these are regular expressions here. One or more?
But only when it's...
I see what you're saying. Yeah, okay, good. Yeah, so she's answering your question. So the plus that you're talking about, that's similar to the star operator, but minus the first term, the epsilon term, is a superscript plus. It's different than the big plus. It's like saying an electron, you know, or a proton is like a P plus with a positive charge. But it's not the same as it's saying a proton plus something else, like addition of a proton to some other. It's a different plus. So when the plus is a superscript, this slide doesn't have any superscript pluses, but it has superscript stars. So when the plus here is in a superscript, it's different notion than the plus here, big plus between two things that you're actually unioning them together. One is a union, the other one is like the clean closure, almost the same as a clean closure minus the first term. But good question, it's two different pluses. So you see, we're getting into issues here when things are ambiguous or notation is overloaded. It happens all the time in real life that words are overloaded and have different meanings in different contexts, and usually you can tell from the context which is which. Sometimes it might arise in a weird way and create confusion, hopefully not. All right, let's talk about some decidable finite automata properties. So given two finite automata, you can answer certain questions algorithmically. So if I give you two finite automata, M1 and M2, and I ask you, is the language of the first empty or not? How can you determine that algorithmically? What's your algorithm to determine whether the finite automata that I give you on a silver platter has the empty language for its language or not the empty language? It accepts something rather than accepts nothing at all. Nothing in sigma star gets it to accept. Well, so you can think about it as a graph reachability problem. If you have a finite automata, it starts here. You want to know if it ends up in some final state using any path whatsoever. If you're asking essentially, is there a path from the start state here in purple to some final state, any final state in red, and if such a path exists, it must accept something, not nothing, right? How many believe that or get that? Now, really, just 10 of you? Let me repeat that. So if you're trying to answer the question of whether a finite automata accepts anything at all, you don't care what, you essentially, in order to answer that, have to determine whether there exists a path from the start state in purple to any final state in red. If there's such a path, whatever the characters along that path are, those characters taken as a string, concatenated together, will cause it to go from the start state to the final state and accept that string, and therefore its language is not empty. And it's an if and only if. How many get that? Okay, good. You had me worried there for a second. No, don't do that. So you can answer that algorithmically pretty straightforwardly. What's an algorithm to determine if there's a path in a graph from a node to another node? Not that hard to do, right? Breadth first search will accomplish it. Start from that start node, mark all of its neighbors, mark all of their neighbors, all of their neighbors' neighbors, and all of the neighbors' neighbors' neighbors. Eventually, if you ever hit the target node, you'll know there's a path. If you exhaust the entire graph and that target node doesn't get visited at least once, there is no path, right? How fast is this algorithm in terms of the size of the graph? If there's n nodes in the graph, n nodes and edges in the graph, how fast does this breadth first search take in general as a function of n, the size of the graph? Wild guess. Yeah, linear. Yeah. How many seed can be done in linear time? Because you keep marking the neighbors and the neighbors, and you don't have to mark anything twice. If anybody points to something that's already visited, look at it, see it's visited, and don't stop expanding from that point on, expand other things instead. Question, will breadth first search work as well as depth first search? If you do a depth first search, will it be just as good as breadth first search? How many say yeah? How many say no? Well, we have votes on either side. Interesting. Graph reachability. You're trying to see if a node is reachable from another node, and your whole graph is given to you. And you want to know if there's a path from a node to another node. And they said breadth first search. Start expanding the wavefront from the initial starting node and see if it ever hits the target node. Now, depth first search, first of all, let me not be presumptuous. What's depth first search versus breadth first search? What's the difference between them? Yeah, instead of expanding as a wavefront, pick a node, then expand it with one other node from it and one other, but you never stop, so you keep expanding, and when you reach some dead end, you go back and keep expanding other directions, right, from the last node, and when you exhaust that, you backtrack and keep expanding. Eventually, depth first search will exhaust the entire graph, will visit the entire graph. How many understand that? So as long as you visit the entire graph, it doesn't matter which order you do it in. So depth first search will work, actually. What if you do some funky search? What if you do some hybrid depth first, breadth first search? First step is breadth first. Then pick a node and do depth first. When you reach a dead end, pick another node and do breadth first from there, and then alternate, breadth first, depth first, and alternating cycles. How many say that will also accomplish this? Yeah, of course. What if you pick a random node to expand and pick another random node to expand and from there and so on? As long as you're kind of advancing the wavefront, it doesn't matter which parts of it are advanced next. As long as it's one kind of continuous, ongoing expansion, eventually you'll know which nodes are reachable and which nodes are not reachable from the original where the expansion started. Okay, so I just want to make sure you understand that. It's not just breadth first. Breadth first works so well, depth first, so will many other types of searches. Those are not the only two. You can make up your own if you'd like. Okay, so in linear time you can answer this question, whether the language of a given finite automata that I gave you is empty or not empty. Question?
How is this different from the halting problem?
So the halting problem is about algorithms or Turing machines, and algorithms have memory and variables, and Turing machine has arbitrary amount of infinite tape that it could use while it's computing. Here you don't have these things. So you don't have to worry about a stack like with a push-down automata. You don't have to worry about an infinite tape like with a Turing machine. You don't have to worry about a big RAM in random access memory, bunch of storage locations or counters or registers or whatever other these machine models have, other parts. Those complicate things, and once you have those things in, you can't do reachability anymore because it's not just whether something is reachable from something, but it depends on the state of the stack or the tape or the memory. And so it's not just a matter of blind reachability in a graph. It depends on lots of other things that are not taken into account while you're doing this expanding wave, and it won't work. In fact, there's no way to do it for Turing machines. For Turing machine, this question is not answerable. It's provably undecidable or uncomputable. Okay. So for example, the halting problem for a finite automata, whether it halts and accepts. I give you a finite automata, I give you a string, and I say, does it hold and accept that string? That's not undecidable. It's perfectly decidable. How do you decide that? What's your algorithm to determine that? One word. Use one word to answer. That forces you to focus on the important word, right? As opposed to saying a bunch of words that hope that something will stick. Simulation. Just simulate it. Or another word is run it. Right? Just run it on that string. Change the states. It's deterministic. It's doing all the right things. And once you exhaust the input, you'll know. In fact, that simulation will run how fast, if the size of a string is n characters, how fast will this simulation run, roughly? Linear time, if you're doing it efficiently. If you don't waste a lot of time, searching for the next state and so on. You may take a little bit extra time to figure out which state is next by going down some table of a transition function, determining what it's going to do next and so on. But even that's constant time per because the machine is fixed. So linear time will do the job. How many see that? So the halting problem is not just solvable for finite automata, it's solvable linear time, which is the best you can hope for. Okay, second question. I give you a machine M2, and I ask you, is its language infinite? So now I'm not asking you whether the language is empty, I'm asking you if the language is infinite. So how would you suppose, now that you're getting the knack of this, how do you suppose you can answer the question whether the language of a given finite automata is infinite or not infinite? Infinite or finite? What's your algorithm now?
If there's a closed loop.
Yeah, find the loop. If there's a loop in this machine, you can loop around it many times, and it'll give you rise to many possible strings that will invoke that loop. But it's not just a loop. So let's say, here's a loop. Why isn't this loop enough? You have to make sure that this loop is reachable from the start state. Otherwise, the loop is not going to do you any good towards accepting an infinite number of strings. It's never reachable. It's like having a subroutine in your code that never gets called. And so whatever it does, it's not going to make or break anything. It's not going to be invoked, so it's as if it's not there. So the loop has to be reachable from the start state in purple. And moreover, the loop itself has to be able to reach a final state. Otherwise, the loop can invoke many times, sure enough. But it's never going to reach a final state, so no strings will be accepted. And so the loop doesn't do you any good again. Right? So you have to have a loop that's reachable from a start state and from which a final state is reachable. Which final state? Any final state. And there's one more condition. The loop must be what? There's something about the loop. It's not just any old loop. Something has got to be true about that loop, yeah. can't be the empty set, in particular the empty string. So, because it's not exactly sets, but still the right idea. The loop cannot have epsilons all the way around it. Because if it did, you'd be going around the loop again and again and again, but all you're doing is picking up epsilons, which when concatenated collapse into nothing, and that doesn't buy you any extra strings. How many get that? So the loop better have not epsilon on the loop, sigma star minus epsilon. It's got to be something other than epsilons on the loop. It's got to be, it could be a few epsilons, but not all epsilons. There's got to be some non-epsilon character on the loop. Question?
I'm not thinking why we want to see if it's infinite, but then want it to be able to reach the final state. Would that be saying it is finite?
So the machine is not infinite. The language of the machine is infinite. In other words, the machine can accept an infinite number of different strings on different occasions, depending on which string you give it. Right? So for any one given string, the machine will always halt, either accept or reject. Just accepting or rejecting that one string. But if you give it a second string, a third string, a fifth string, a Google string, it'll do accept or reject for each one of those. The question is, how many strings in sigma star, and sigma star is an infinite number of strings, will cause it to accept? Finite number or infinite number? That's the question. So it's a pretty deep question because there's an infinite number of possibilities. But this answers it in one fell swoop without testing them all out. Right? Let me give you a non-algorithm for this. So this is an algorithm, and you can run it pretty efficiently. I'll let you think offline. How long does it take to find such a loop? Then see if it's reachable from a start state. Then see if it reaches a final state using some other path. So there's a bunch of graph reachability path problems embedded in this problem. Several different ones. How many see that? Right? And you can run them all, and it'll take a while. But you can do this. It's not going to be an infinite number of possibilities, or there's only a finite number of states there. There's only so many loops you can have there. Check them all, and if you must, and then you'll know if there's something of this form. Question?
Could you use like a loop when you're looking for graph reachability?
You could be stuck if you're not careful, right? If you're looking for a restaurant on this block, you know it's on this block, but you're looking for it, you don't know if it's there or not. Could you, if you're not careful, circle around the block forever, drive around the block forever looking for that restaurant? Yeah, if you're not careful. But there's a way to avoid that, right? Keep driving around the block, look at more and more businesses and see if each one is the restaurant. And if you ever reach a place that you've been to before, abort the search, and then you'll know that it's there or know that it's not there. So yeah, of course you can run forever if you're not careful on almost anything. But if you're just a little cautious and save yourself the risk of running into a different loop, you can easily avoid running forever. And that's, of course, what we do when we write algorithms or codes. So just because there's a cycle in it doesn't mean you have to spend forever finding the cycle. Right? Just like, you don't have to drive around the block forever, even though you could. It's just not a good idea if it can be avoided. Yeah.
For question 2, can't
Yeah.
you use the convert to regular expression and then see if there's any clean closures or the plus signs?
Excellent question. He has a different algorithm. He says, convert this machine to a regular expression. And by the way, how do we do that? Well, a few slides ago, we had a technique to do that using generalized finite automata. Then look at a finite automata and see if it has any clean closures in it. And if it has a clean closure, presumably it's infinite. If it doesn't have a clean closure, it's finite. How many understand this algorithm? It's a very good idea. In fact, that almost works. It's 99% there.
When you just told us he has a superscript plus as well as a
Well, so that technique from a few slides ago only uses clean closures, not pluses. But still, it's almost there. You can make it work, actually. There's one issue here that's a bit unresolved right this second as we stated it. But it's 99% correct. What is missing here? Not a huge thing, but it's a technical issue, but without that, it won't quite necessarily be guaranteed to always be correct. Again, his idea is this. This is a great one. Convert this machine to a regular expression, and then the regular expression, see if there's any clean closure, and then you'll know if it's finite or infinite, the language represented by this regular expression. It's a great idea.
You can't have an empty string.
Yeah, if that clean closure applies to something that's just the empty string inside, it's not going to get you an infinity out of that. You'll just get an empty string over and over again, and just because there's a star there doesn't mean it's infinite. But if you're careful to observe what's the clean closure being applied to in that regular expression and what's inside, better not be an empty string only, Could it be empty string plus other things? That's okay. But as long as it's not empty altogether in terms of an empty string inside the expression as being clean closure applied to, then you're good. And that's equivalent to this condition here, right? So this loop. This loop cannot have all epsilons around. So it's sort of the same issue as this algorithm here. But that's a completely different algorithm than this. This is about graph reachability. His was about converting to regular expression. So now you have two algorithms and two different proofs why this is decidable. Excellent. I should give you extra credit just for saying that. That's great. In fact, I will. Submit that to the class website, extra credit. So I want to encourage you to come up with stuff in real time. All right, what else? Should start doing it more often, right? All right, here's the one that's a little more subtle even. I give you a machine M1 and a machine M2, two machines. I hand them to you, two finite automata. And I ask you, is the language of the first the same as the language of the second? And both languages could be infinite. So what you don't want to do is go through all of sigma star and test each and every string on both machines and make sure that for every string, both accept or both reject. What's wrong with that non-algorithm? What's wrong with what I just said if that would be my solution? Yeah. You'll never end. There's an infinite number of strings in sigma star. You can't possibly test them all, and then you'll know because there is no after infinity, and so you'll never know. So that's not going to work. You can't test them on all cases. You can convert to regular expressions, but then you have to determine whether two regular expressions are equivalent. And that's not obvious at all how to do that. It turns out you can do that. It's just very, very complicated. And in fact, we don't know how to do that in polynomial time. But here it's not even the issue of time. The issue is whether you can do it at all, even inefficiently. What else do you say? Yeah. But that language could be infinite. So you're going to feed all infinitude of these strings in the language of the second machine, which will never halt. And so when will you know? Because there could be an infinity of strings in that language. So feeding each and every one of those strings with the second machine would take forever. Literally forever. Not just exaggerated forever and say something took forever. It'll literally never end. Right? So, but it's a good try. What else could you do? Yeah. Yeah, you can take the intersection of the language. So here are the two languages, L1 and L2. And now we're not talking about the language anymore. Two sets, L1 and L2, arbitrary sets. Two sets are the same if what is true about their union and about their intersection. They're the same. Two sets are equal if their union is the same as their intersection. It's an if and only if, right? So here's their intersection, and the union is all of this, all the colored region here. And if the intersection of two sets is the same as their union, it can only happen if the two sets coincide. Another way of saying it is if the difference of the two sets is what? The two sets are the same if their difference one way and the difference the other way. Two sets L1 and L2 are the same if L1 minus L2 and if L2 minus L1 are both what? Empty. How many get that? The two differences must be empty. If the two differences are empty, they're one and the same set. So look at this. Here they're not the same, and the difference is not empty. The difference of one minus the other is all the red region that's not in the yellow. It's all this stuff here. The difference of one minus the other direction, is all the yellow stuff here that's not in the red. All right? But if both were the same, the difference one way will be empty, the difference the other way will be empty. It's an if and only if. So now you got to just determine whether the two differences are empty or not. How do you determine whether a language is empty or not? What's your algorithm for determining if a language is empty or not? I'll give you a hint. It's on this slide. It's the first problem, right? I mean, we just did that. So construct the difference of the two languages in terms of two machines, and then invoke this first subroutine twice, one on each case, and then you'll know. And then they'll be the same if and only if both are empty languages. The only loose end right now is how do you construct the difference of two languages in terms of a machine? If I give you two machines, how do you construct another machine that accepts the difference of the languages of the first two machines. How do you do that? Two words. Cross product. Good. Excellent. How many see cross product construction? Only a dozen people. Okay. All right, let's go back in time. So now we're going backwards to a couple of lectures ago. Right? Finite automata. Right? We just defined them here. Here's the J-flap. Okay, and we said intersection preserves regularity, and that was a cross-product construction. How many remember that slide from a couple lectures? Okay. Really? It was just 20. How many remember this slide from a few lectures ago? Okay, that's better. Are you just saying that because I'm forcing you to, or do you really remember? Never mind, don't answer that. But from the cross-product construction, what we did very quickly is proved a whole bunch of other theorems in quick succession. Right? We proved all these other theorems, and one of them was set difference. Right? Two languages, the difference of two languages preserves regularity. If two languages are regular, the difference is regular too. Why? Because but set identity, which is L1 minus L2 is the same as L1 intersect L2 complement. So we know that complementation preserves regularity by inverting final and non-final states, right? We know that intersection preserves regularity. How do we know? Well, that was a previous slide, right? Cross-product construction. And because the difference of two sets is always the intersection of one with the complement of the other, that's not about language, it's about sets. That's an identity for sets. How many get that? It's true about any pair of sets, right? That their difference is the same as the intersection of one with the complement of the other, if you think about it, right? So you can either do that with cross-product construction, right? Or you can do that by using the set identity. But even the cross-product construction, let's do it the hard way, create the cross-product, but you're accepting the difference. So you accept something that's in the first, but it's not in the second. So all your final states will be something that's in the first, but not in the second. The final states will be all the final states of the first crossed with all the non-final states of the second machine right here. And that'll get you the difference machine. The machine that accepts the difference between the languages accepted by the original two machines. Right? How many get that? Okay, I'll take it, about half of you. Any questions about that? So we've already done this, right? This is about 3 lectures ago. So again, what are we doing? We have two machines. We want to create a machine that accepts the difference of the two languages, respectively, of the other two machines that we started with. So create the cross-product construction, bang together the two sets of states, and the resulting simulating cross-product machine will simulate both machines simultaneously. And how do you get the difference? Is by this construction, this crossed machine, this simulator, if you will, accepts all strings that the first accepts, but the second one doesn't. So these strings right here, the double states, double final state, when you reach here, it will not be an accepting state in the crossed machine. How many get that? You got to be accepting in the first, but not in the second. That's what the difference is. The difference between the two sets is all the things are in the first set, but not in the second set. Because those get subtracted away from the first set via the difference operator, right? That's what difference does for sets. It takes away elements. It doesn't add them like the union. Okay, so now fast forward in time to the present. And we have an algorithm, right? We can construct a machine for the difference one way, L1 minus L2. Separately, we construct the machine for the difference the other way, L2 minus L1. And then we send both of these machines to the first algorithm that determines if their languages are both empty. And then we'll know that the two original machines had the exact same language that they both accept. One the same as the other. How many understand this strategy, this algorithm? It's really an algorithm. And so we are able to decide whether such a property is true about two machines. For Turing machines, you can't do that. It's undecidable. For finite automata, you can. We just did this. For push-down automata, which we're about to describe next, you can't do that again. It's undecidable. There's no algorithm in the universe to do that for Turing machines or for push-down automata. But here, there's an algorithm. We just described it. So you should read about it in the book. You should read about it on Wiki or wherever you can find other explanations of what I just said in the last 10 minutes. You should reinforce that by reading other sources. How many go to Wikipedia occasionally? It's a good thing to do. Great, most of you, excellent. Do that a lot. There's really good stuff out there. Or to Khan Academy, or Udacity, or edX. There's lots of lectures about all this stuff online, other than the ones I'm putting on. But it's good to hear it from different people, different explanations, different points of view, different ways of explaining and defining things. It's all the same stuff, just different ways of explaining it. Some explanations might click better when you hear it 2 or 3 different times from different sources. That's all. Okay, any questions about any of this? And you can name other properties. We named 3 properties here, 3 questions for which we just gave algorithms to determine them one way or the other. And right now we don't care about efficiency, by the way. These algorithms, some of them can be very inefficient. That's okay. They're still doable. That's fine. Later in the course, when we start talking about NP-Completeness and interactability and efficiency, polynomial time versus non-polynomial time, and deterministic polynomial time versus non-deterministic polynomial time, all that good stuff, NP-Completeness, then we'll start worrying about efficiency more than we do right now. Right now, we're just concerned with what is possible, not how efficiently can it be done. Because, look, if something is impossible, it doesn't behoove you to try to do it more efficiently, because you can't do it to begin with, because it's impossible. So if you can't prove that it's possible to begin with, there's no point debating how efficiently or inefficiently it might be doable, because it's not doable to begin with, not even inefficiently. And that's sort of the stage we are now. Later in the course, when we have more machinery, more infrastructure, more theorems, more mathematical concepts wrapping our minds around, then we'll be able to prove more sophisticated things about efficiency as well. And that'll get more complicated. But right now, we're just wondering what's possible, what's not possible. All right, so I already said that, minimizing a regular expression to the smallest possible size, it's doable. There's an algorithm for it, and I urge you to try to figure out an algorithm for it. But it's piece-space complete. It's actually worse than NP-complete. We don't know of any efficient algorithm to do this. We know of lots of inefficient ways to do this. For Turing machines, finding the smallest Turing machine, minimizing the size of a Turing machine is undecidable. Similarly, minimizing the size of a program, a computer program, undecidable also. It's not solvable. There's no algorithm for it. So if I say write the smallest possible program to do something like produce prime numbers or Fibonacci numbers or multiply matrices together or whatever, and I say find the smallest possible and prove that it's the smallest, in general, it's impossible to do, proving that something is the smallest. We're actually going to prove that later on in the course. All right, and that brings us to context-free grammars and context-free languages, which is the next more sophisticated machine models beyond finite automata. Any questions before we dive into this deeper pool here? Yeah.
You could prove that in specific cases, though, right?
Oh yeah, for specific cases, you can prove that something is the smallest. For example, the smallest program that does nothing is just, main, open paren, close paren, open brace, close brace in C, for example. 8 characters. Can't do any less because the word main has got to be there, otherwise the compiler will throw up. So, yeah, of course, in smaller cases, you can do that. And in specific cases and in more obvious cases. So the halting problem doesn't say that you can never do this, never solve the halting problem, or never minimize a machine, or never minimize a program, right? If I want to have a program that adds 2 numbers together and does nothing else, again, there's a few lines, a few characters of code that will do that, and you can prove that that's the minimum. But in general, it's undecidable. All right, so context-free languages. In the book now, we're entering chapter 2, page 100. You should be tracking the book offline, reading the book, and looking at the book. So context-free grammars, the basic idea is you have a set of variables and a set of production rules relating those variables to how to change these variables into other variables. So the variables here in the grammar track the states in the finite automata, essentially, right? And so you have a finite set of variables, a finite set of terminals. The terminals are dead-end variables. In other words, the specific values, like the alphabet in your finite automata or language. You have a set of production and a start symbol where the grammar starts, and the productions basically substitute things for other things, right? So we say VI goes to delta. Delta is some set or sequence of variables and or terminals, and so V union T star, so this is a regular expression denoting all possible juxtapositions of variables and terminals in all possibilities, and delta here is one of those string combinations of terminals and variables. And basically it says that if you have some VI here, you can substitute delta for it. This rule says substitute delta for VI. VI becomes delta. That's why the arrow is kind of pointing from the VI to the delta, because it transforms, changes, or substitutes the delta for the VI. And it's a local substitution rule. It doesn't depend on the context. It doesn't matter what's on the left or on the right of this variable VI. That's why it's called context-free grammar, because it doesn't depend on the context. It's free of the context. The opposite is context-sensitive grammar, which means it depends on the context. Right? A lot of things in life are context-sensitive, like humor, for example. Right? You have to pick your humor very carefully based on the context. If you're with your drinking buddies in college, you're not going to make the same jokes as you do if you're appearing on some nationally televised, competition like the Olympics or whatever. You have to be a lot more cautious. Right? So humor is context-sensitive. But certain things are context-free, like justice under the law. It doesn't matter who you are, or how much money you have, or, at least in theory it doesn't. In practice, we can have a long debate about it, right? But, so here, this context-free doesn't depend on the context, what's on the left, what's on the right, where it's coming from. You can just substitute it locally and don't care, yeah. Yeah, so productions, you can have the same variable produce several different substitution rules, and you can apply any one of them that you want randomly or non-deterministically. We'll talk about that in a second. But you can have multiple productions going off the same variable or involving the same set of variables or whatever. There's no restrictions on what production rule could look like, as long as there's one variable on the left of the arrow and some concatenation of variables and or terminals on the right-hand side in any combination you want. So it's always one on the left. For context-free grammars. Now, for context-sensitive grammars, you can have more stuff on the left. You can say A, V, B, going to something. That means V can go to that thing, but only in the context of an A and a B. If it has something other than an A on the left or other than something other than a B on the right, it ain't going to happen. It's not going to fire or trigger that production rule. It's a good question. So that's one of the differences. Other questions? All right, so let's give you an example. So here's a grammar. S goes to SA, it goes to SB, or to epsilon. What's the language of this grammar, would you guess? Just looking at this simple, short grammar, 3 production rules. What will be produced by this grammar in terms of strings of terminals when all is said and done when you start with the S? It's not a hard to just kind of eyeball it and guess. Yeah. Any combination of A's and B's, right? How many can see that, right? Right? You want an A, fire the first rule. You want a B, fire up the second rule. And if you want to terminate, fire up the third rule. And so, for example, here's our derivations, right? S goes to SA, that fires up, triggers the first rule. And from S then goes to epsilon, that triggers the third rule, and you only end up with an A. Right? Here's one that ends up with AA, BA, using this triggering of the rules. Right? And you can end up with any string that you like in sigma star. So the language of this grammar is sigma star, right? Because the language of a grammar is defined simply as the set of strings that this grammar can generate under any circumstances whatsoever you choose. So if a string is generatable from the grammar, it's in the language of the grammar. If it's not generatable from the grammar, it's not in the language of the grammar. That's how you define the language of a grammar, right? So I'm saying that right here very explicitly. The language generated by context-free grammar is a set of all strings derivable or generatable in the grammar, starting from the start state and ending up wherever you'd like. And triggering the rules in what order? Not a trick question. Which order are you going to trigger the rules in if it's ambiguity? Whichever order you'd like. All bets are off. You get to choose. It's not deterministically. But if there's some way to trigger some set of rules to derive a string, it's in the language. Right? That's all it is. So here's another. So the language of this grammar is sigma star, is what we're saying here. All strings are derivable from this simple grammar. All right. So a language is said to be context-free. Now this is a definition. Definitions are in purple. A language is context-free if there exists a context-free grammar that generates it. So So context-free language is not the same as a context-free grammar. Context-free language is, first of all, it's not even the same kind of object. One is a language, one is a grammar. One is not the same as the other by type. But if a grammar produces a language, and that grammar is context-free, then that language is context-free. So it's two different objects, grammars and languages. But they're the same. They represent the same sets, I should say. Okay, so that makes sigma star, AB star, a context-free language. Now, it just also happens to be regular as well. How many remember that sigma star is also regular? Yeah, of course, it's a finite automata that accepts all possible strings. Right? Start state and go to the start state, and that's also the final state, and don't go anywhere else. And you've accepted sigma star using a finite automata, so sigma star is also a regular language. But it's also a context-free language because there's a grammar for it, and here's a grammar for it. Now, it's not necessarily a unique grammar. In fact, no grammar is unique. There's also sorts of other grammars that accomplish the same thing. They'll accept sigma star. They could be longer, more complicated, more production, but they'll do the same thing, just like in programs. Right? If you write a prime number program, there's lots of other programs that will also produce prime numbers, and those are much longer and more complicated, more convoluted, with lots of stuff in them and different algorithms maybe, but they'll all have the same output, prime numbers. So programming is not unique, and neither is grammars. Right? Just keep that in mind. Okay, a palindrome reads the same backwards and forwards. So for example, the word civic spelled backwards is civic. Right? The sentence, step on no pets, read backwards, says step on no pets. That's kind of cute. There's even entire poems that are palindromes, entire novels, actually. That's hard to do, right? Look it up. It's kind of cute. But the point is, the set of palindromes is context-free. And to do that, we have to come up with a grammar that generates them, right? So a palindrome is something that reads backwards and forwards. So W is equal to WR. WR is the string W reversed, written backwards. Okay? So how would you come up with a grammar, context-free grammar, that generates exactly the palindromes and no non-palindromes? The palindromes and only palindromes. Well, not too hard to do. Here's a grammar that does the job. S goes to ASA. Little a's in blue are terminals. They're characters in the alphabet. Or it goes to BSB, or to A, or to B, or to epsilon. So there's 5 production rules. 1, 2, 3, 4, 5. And by the way, these 5 production rules, I'm stringing along as one giant single line rather than having S goes to this, then separately S goes to that. In the previous slides, I actually wrote it as separate rules here. But I could have written them on one line if it's the same left-hand side that goes to all these right-hand sides. I might as well just shorthand it. So instead of writing it this way here, I'm writing it that way there. It's equivalent way of denoting it, just a little more succinct, because you don't have to say arrow and arrow over and over again separately for the same characters. So that's what I'm doing here. So here's some sample derivations. I fire the first rule, goes to here, then this S gets triggered on the second rule and substitutes a BSB for the S here. This substitution here is the second rule right there. And then this last substitution, S goes to epsilon on the 5th rule, and you get ABBA, and sure enough, it's a palindrome, ABBA. And then, of course, you can do other derivations, and here's a derivation that does BAA, another palindrome, and you got a separate, different set of triggerings of these rules in a different order. How many get this? Pretty straightforward, right? Basically, the strategy in this grammar is you have this central symbol, that's the variable, the current variable at any given moment, and it keeps shooting off to the left and to the right, A's or B's in equal numbers. And once you do that for a bunch of times, you can't help but have a palindrome on your hands, because you're going symmetrically mirror image left and right in the same kind of character generation rules. So you will get palindromes, and you will get all the palindromes. Any questions about this? So the set of palindromes is a context-free language because there's a context-free grammar that generates it. Okay, for example. Yeah.
What's the difference between like the ASA and just the S?
Right here.
So like, what does that do?
It takes S and substitutes for it ASA. So that S disappears, and instead we substitute this right-hand side of the rule. It's like saying substitute X for Y. So take away the X, put Y instead, and that's the substitution rule. So here, this is X, and this is Y. That's all.
What about
So these other ones are also rules that you can substitute S for alternatively. Instead of substituting ASA for S, you can substitute BSB for S instead. And if you want to use the second rule right here instead of the first, be my guest, you can do that. Or the third or the fourth or the fifth. So basically, I'm saying these are multiple rules. So here I wrote them separately. S can be substituted with SA, S can be substituted with SB, or S can be substituted with epsilon. But because S can be substituted by either one of these three things, I wrote it together on a single line like that. That's all. I made it more succinct. Save me a few characters of typing, more S's and more arrows like I did here. But this grammar and that grammar is the same grammar. I just denoted slightly more compactly, that's all. Yeah.
So far, we've been working with these grammars that just have the start character and then some other stuff like A and B, and then there's always one with S and epsilon. We get rid of the S at the end. Well, what exactly are the rules for executing one of these grammars? You have to keep going until the end.
No, you don't have to keep going, but if you don't keep going, you haven't generated a string because there's still variables in there. A string must be only containing terminals. And that's the alphabet of the language, all the terminals. It's like the sigma in regular expressions or regular languages or finite automata. So if you don't create a situation where everything is a terminal, you haven't finished generating, and if you stop, it's a non-generation situation. You haven't generated a string. You just got.
So A and B are terminals, S is a variable, and we haven't seen any other variables.
And this grammar doesn't have any other variables besides S. But other grammars can have other variables too. And we'll see some examples where that might be the case. Yeah.
So context-sensitive languages, as opposed to that you have like, rules like AS goes to something.
Yeah, so context-sensitive language can say AS goes to an SB, for example. And it won't trigger unless there's an A on the left side of an S. And if there isn't, you can't fire that rule. It includes context, right? Just like you can't make, an off-color joke on national news. Well, you could, but you'll suffer the consequences of doing that. Any questions about that? Any other questions or issues? Okay. So we just finished saying that the set of palindromes is a context-free language. And let's design a context-free language or context-free grammar that represents all strings of well-balanced parentheses. Well-balanced parentheses, you sort of know what it is. When you open a parenthesis, you have to have a closed parenthesis. It can be nested or juxtaposed. So here's a grammar that generates all well-balanced parentheses. S goes to SS, or to parentheses S parentheses, or to epsilon. So for example, you can derive this string here made of these parentheses. So the alphabet is left parentheses and right parentheses, not A and B, but the two parentheses. That's the alphabet. Two characters, two terminals in the alphabet. So you can say S goes to parentheses, S goes first of all to SS, like this. This first S goes to the second rule, triggering the parentheses S parentheses. Second rule here gets triggered again. And then both of these S's, using the third rule, go to epsilons. The epsilons vanish. Everything is a terminal now. You have parentheses open, close, parentheses. That's a well-formed, balanced parentheses. And that's a string, and that's all terminals, and that's a string in our language. Here's another derivation where S goes to parentheses S parentheses, and that rule gets invoked again, the second rule here, second generation rule in blue. And then this next S goes to an epsilon. The epsilon vanishes because it's an epsilon. Concatenation of epsilon to anything else is that anything else without the epsilon. And then you have this kind of parentheses, open, close. And here's yet another one where you have open, close, close, close. The point is it's well balanced. What you will not get out of this grammar is open, close. That's it. So two opens and one close. That will not be derivable in this grammar. How many can see that? Because the second rule, when something opens, it must close too. You must take them in pairs. And you can either nest them. This is a nesting rule. Open, nest, close. And whatever that nesting is can be more well-balanced parentheses. Or this is a juxtaposition rule, where you can juxtapose two well-balanced parentheses, and together there'll be still yet one more well-balanced parentheses yet again. So you have nesting rules and juxtaposition rules, and together, in any combination, that'll get you any well-balanced parentheses combination. But you will not get non-well-balanced parentheses, like open, close, open. That will not happen here. So this makes the well-balanced parentheses as strings a context-free language. Here's another alternate grammar for it, parentheses S, or epsilon, right? And it turns out this grammar is equivalent to the first. It's a little shorter. It's only 2 production rules. It's also less characters if you count them all. And this will also generate well-balanced parentheses, and it will generate all well-balanced parentheses and no non-well-balanced parentheses. It's just harder to see from the way this grammar stands, but it's the same. It generates the same language. So this illustrates the fact that just when you think this is the shortest possible grammar for well-balanced parentheses, there's a shorter one, but it's harder to see that it does the same job. How many can see that this does the same job as this grammar? You can sort of see it, but you have to prove it. You have to. It's not. You can't just scratch your head and say, "Oh, I think it's the same." You got to be able to argue that for every string that's generatable from the first grammar, the second grammar generates that string, and vice versa. If the first grammar doesn't generate a string, it's not generatable in the second either, and then the 2 languages coincide. It's something that you need to prove. It's not that hard to prove, but you can't just wave your hands and say it without some proof. Okay, so design a grammar, a context-free grammar generates regular expressions. Remember, regular expressions, they're strings. They denote regular languages, but they're not languages themselves. They're strings. Question?
For showing that 2 grammars produce the same things, can you show that
Oops.
you can produce each of the production rules of one from the other?
You don't do it based on production rules. You should do it based on strings that get generated and not generated. So basically, you have to argue, if you want to argue that 2 grammars produce the same language, you want to show that both grammars produce the same set of strings. So you want to be able to show that every string producible in the first is producible in the second, and vice versa. Each one can produce the strings of the other one. And if you show that, they produce the same language. If you think about it. Another way of saying it is, the second one must produce all the strings of the first one and none of the strings that are not in the first one. Whichever way is easier for you to argue. It's like showing 2 sets are the same. How do you show that 2 sets are the same in general? Not languages, not strings, not grammars, 2 sets. How do you show that set A is the same as set B? Show that one is a subset of the other, and show that the other is a subset of the first. And 2 sets are the same, even only if each one is a subset of the other. That can only happen if they're identical sets. Otherwise, one might be a subset of the other, but the other won't be a subset of the first. Okay? So you break down the theorem into 2 sub-theorems, or lemmas, if you will, and same thing here. You break the equivalence of 2 grammars into 2 situations, 2 scenarios. Show that every string producible by the first is also producible by the second. Separately, as a second matter, show the opposite. And now you have 2 set containments. And if 2 sets are contained, each one is contained in the other, the 2 sets are one and the same set. Same principle as sets. Remember, languages are sets. So whatever is true about sets is true about languages in general. Right? You know, zebras are mammals. So whatever is true about mammals is true about zebras. But not necessarily the other way around. Whatever is true about zebras is not necessarily true about all mammals. Like, not all mammals have stripes, even though zebras do. Right? Question?
Can you clarify the syntax where it's like L parentheses G1?
Yeah, so all this is L of G1 means the language generated by that grammar G. That's all. It's just notation. So we've been saying that all along, but it's written like that. So the language of G1 is the same as the language of G2. That means that the language generated by the first grammar is the same as the language generated by the second grammar, and its equality is about sets, because each side of the equality is a set of strings, it's a language. That's all. All right, so here's a context-free grammar that generates all regular expressions. So you have the nesting rule here, the first rule, then the second rule is the juxtaposition rule, the third rule does the clean closure notation, the third rule does the union notation. So for example, here's a derivation. S goes to S star. This S goes to parentheses, S parentheses, that's the first rule. The first rule was the third rule, right? S goes to S star. And this rule here was the second rule, the first rule here, S goes to parentheses, S parentheses, right? And then S goes to S plus S, that's the fourth rule invoked here, from here to here. and then S goes to A and S goes to B. That's these rules here. S goes to any terminal from the alphabet of the language. And together, that gives you A plus B star. This derivation here will give you A, B, A star A. And basically, we're saying that the set of regular expressions taken as a language, where this expression is a string, is a context-free language. Because here's a context-free grammar that does the job. How many get that? Okay. Now, that's not to say that regular expressions, a regular expression gives rise to a context-free grammar or a context-free language, even though technically it does. Don't make type errors. Be careful not to make type errors. So now we're talking about regular expressions as if there were strings in this language that represents all regular expressions, all strings corresponding to regular expressions. Yeah.
This might be a silly question, but I thought there'd have to be like epsilon in order for like the context-free grammar to like terminate. So since there's always S, it's always going to have to do one of those S.
Okay, so yeah, as you said, the grammar must generate strings that are terminal. So A is a terminal string, B is a terminal string, so is star a terminal string now. Yeah, so the alphabet contains A's and B's and pluses and parentheses and stars. Those are all characters in the alphabet. Okay, so what you get is all possible regular expressions from this derivation rules. Any other questions about this example? Yeah. Yeah, I should have included those characters in there as well. So here I included the A's and the B's, sure enough, but I should really include the pluses, the left parentheses, the right parentheses, and the star operator as well. So you know what? That's essentially an error on the slide, so extra credit. So at the beginning of the course, I said if you can find errors in my slides or even minor omissions, I try to be very precise. I don't always succeed. I try to. But if you can find errors or omissions on the slide or technical incorrectnesses, extra credit. So send an email or submit the extra credit claim to the class website, and good for you for noticing that. Excellent. Any other thoughts or questions? Yeah.
Why does the star and the plus and the parentheses have to be in the language that they're already accounted for in our production?
Well, so it's regular expressions over the alphabet sigma, but technically the alphabet of this language must have these characters in it. These are regular expressions that denote languages that are only for sigma equal to A and B. But that's not the complete alphabet for the language of this grammar G. It's only of the languages that these regular expressions of strings in G denote. So again, it's a subtle indirection or type situation. That's all. But that's a good point. So the languages that these regular expressions denote only contain an A and a B in their sigma. But the sigma of this language here, denoted by the grammar G, must also contain A and B, and parentheses and close parentheses and plus, to be technically complete about it. Now, if you're saying that I intended to make this alphabet pertain to the other languages that these regular expressions denote, then technically it's not an error. But really, what I should have included that in the slide to be completely correct about it and complete about it, so it wouldn't be confusing. So if I confused you, I apologize. I try not to do that. Question? Yeah.
Basically, clarification. There should be two languages on this slide. One, which is sigma L, which is just A and B, and one, which is sigma G, basically, which is
That's right. Yeah. Yeah. So let me correct that. You said two languages. It should be two alphabets. Yeah. Okay. So you corrected me. I corrected you. We're good. You still get extra credit though, because you're the one who noticed that. Okay. Any other thoughts or questions? All right. Let's talk about ambiguity. So ambiguity is not a great thing in languages, just like it's not a great thing in real life. Here's the word ambiguity written the same upside down, which is kind of interestingly, artistically difficult thing to do. So, if you say, I like dominating people, that be construed as verb or an adjective. Think about it. two very different meanings. If you say, I like annoying people, the word annoying and I like annoying people could be construed as a verb or an adjective. So do you like people that are annoying, or do you like to annoy people? So that's ambiguous statements, right? And that's not good with respect to being clear on your intentions and meaning. In arithmetic, there's examples, a minus b plus c. Is it a minus b and then c added, or is it a minus and then b and c added first? And those have two different meanings, arithmetically or mathematically. In programming environments, if you say if P then Q, if you say if P then if Q then S else T, it could be parsed this way with parentheses around the second if, or it could be parsed with parentheses around this if here, and the then and the else could be grouped this way or that way, and it's not clear which from the context unless you have very strict rules about priority and order of operations. So these are all examples of ambiguity, right? And generally, you want to avoid ambiguity. So we're about to talk about ambiguity in grammars, but first let's talk about ambiguity in language. These are actually signs that you see in real life. Eat here and get gas, right? I mean, that is an ambiguous situation, right? From the context, they probably didn't mean, the medical emergency kind of situation, but no parking violators will be towed. So it could be parsed as no parking violators will be towed, or no parking violators will ever be towed, which means you have free pass to park there if you want. Call me a cab. Okay, you're a cab. That's actually a line from a movie. I don't know if you've ever seen that movie, but right? We love hurting people, right? Hurting could be a verb or it could be an adjective, and it's very, very different meanings, right? The song Lola by the Kinks, last line says, I'm glad I'm a man, and so is Lola. It's not clear if Lola is glad he's a man or he's glad that Lola is a man. Probably both, if you know the song. That's okay. No judgment here. But ambiguity in art, also fascinating, right? This could be a rabbit if you're going kind of left to right, but right to left, it could be a duck. How many can see the ambiguity there? Good. Some of them are not easy to see. How many can see a dog in this picture here? There's a dog in there. Dalmatian kind of spotty dog. If you kind of squint your eyes, sometimes if you squint your eyes, it's easier to see the ambiguity, right? Here's kind of an ambiguous figure in ground. Here's Don Quixote, right? There's a windmill here, but it's really his hair. And this is his mustache. Or if you look at this as a horse and rider, that's the lance that he's carrying. How many can see that ambiguity? It's a little more subtle. A skull, it's really two people, but it looks like a skull. Same here, two people riding a sleigh, or really a kind of a skull there. Here it's hard to tell if the face of the hound is looking left or is looking right. Right? How many can see that ambiguity? Depends on how pretty cute, right? So in art, ambiguity could be interesting, artistic, cute, compelling, mesmerizing even, right? Here are some landscapes, right? Escher, Maurice Escher, the artist, played a lot with ambiguous figure and ground kind of situations in his etchings. Here's the word optical illusion embedded as figure and ground together. Here's good and evil. Evil being the spaces in the good and vice versa. Good is kind of wrapping up the evil. It's interesting embedding, right? Two very opposite concepts. So ambiguity could have its uses, including art as we just saw here, but in languages not so much. So a grammar is ambiguous if some string in it could have two different non-isomorphic derivations. So for example, in the language of sigma star that we saw earlier, this grammar, S goes to SS or epsilon, this one's not even sigma star, it just generates only epsilon. But it can generate epsilon in lots of different ways. S could go to epsilon or to SS to SSS, and each one can go to epsilon from the second rule. And when you do that, you get just more and more epsilons. But here's a grammar for the same language, epsilon, that is not ambiguous. So sometimes you have ambiguity in the grammar. How many can see this grammar is highly ambiguous, right? There's lots of derivations, all of which produce epsilon. But ideally, you want every string to have a unique single derivation and no other derivations that are different than it. Just like in English, you want to be able to parse an English sentence exactly one way, ideally. But we already saw examples of the contrary. So English is not an unambiguous language. It's highly ambiguous. Right? And here's sigma star. S goes to SS or to A or to epsilon, which means it produces a sigma star, or in this case, A star. But there's lots of ways to generate AA, including lots of other derivations where S's will just become epsilon. So ambiguity is not great in languages or in grammars, especially in formal languages or in programming languages. Otherwise, the compiler, think about it, if your programming language is ambiguous, it's just a language. Your strings are your programs. If a programming language is ambiguous, you might make a statement and the compiler may interpret it different than what you intended because it's ambiguous. And then you'll have a very subtle bug in your program because you think you meant what you said and you did, but the compiler interpreted it something other than what you said because it can be interpreted multiple different ways. And next time we'll go more into ambiguity and how to avoid ambiguity if possible. And we'll see also that some languages are inherently ambiguous. It's a problem that the language has that ambiguity cannot be avoided whatsoever. So we'll talk more about that next time. All right, any other questions? Yeah.
What do you mean by isomorphic?
What's that?
Isomorphic?
Oh, isomorphic means that two derivation trees are different topology. It means that derivation is inherently different. It's not the same derivation. Different sequence of deriving, basically. Yes. All right.
I have a question.
Yeah.
Can you prove that two algorithms are equivalent?